Hi, this is Patel. In this lecture, we are going to learn about the concepts of the torsions. What is torsion and how is this applicable in the real design and where it is applicable, as well as the concepts of the torsions is clubbed with the example where you will find the application of these concepts in your examinations. Okay, so this lecture is going to give you the brief idea about the torsion phenomena. So let's get started with the first slide, which indicates the definition of the torsion. And the definition of the torsion can be asked in your examination into 1 to 2 marks. So it will help you to understand this torsion word, term and the phenomena. Okay, so what is torsion? When the shaft is subjected to a torque or a twisting moment, they get twisted, and this phenomena is known as a torsion. In this diagram, I have shown one shaft whose cross section is rectangular. The cross section might be changed according to the application. Some shaft might have the cross section of a circle or square, rectangle, triangle. Based on their application, their cross section can be changed. But right now I have taken this example of the rectangular cross section shaft. Now if you apply the twisting moment or the torque on the shaft, then it will get twisted, and this twisting phenomena is known as a torsion phenomena. And this occurs whenever we utilize the shaft as a power transmitting element. Whenever we want to transmit the power from the one end of the shaft to the another end of the shaft, it will there is a high chance of there is a high probability to get twisting of the shaft, and that's why we need to find out the effect of this torsion, the stress is generated due to the torsion phenomena, as well as we need to find out that how much amount of the stresses that the shaft material can carry during this condition. And that's why this is very important while designing the shaft. Okay, now we will see another slide where you will find the theory regarding the assumptions of the shear stress due to the torsion. Now whenever we find the stresses generated due to the torsion, there is the first stress that comes into the picture is the shear stress, which is the most important stress while designing the shaft. And that's why you need to find we need to find a few assumptions which will simplify the findings of the shear stress, or simplify the equation of the shear stress, so that we can understand the concept of designing method of the shaft. So let's see what are the assumptions that can be asked in your examination in your to design a shaft in the torsion phenomena. So the material of the shaft is uniform throughout. So we have assumed basically that your material is homogeneous and isotropic, just as the similar as the we have assumed in the bending theory, pure bending theory. Now the second assumption is that the twist along the shaft is uniform. That we have assumed that if the shaft is having the length of the L, let's say L, if this much amount of long shaft is available, then if you apply the twisting moment over this end and this end is fixed, then the twisting of the whole shaft is uniform. Then it is not like that you have applied the twisting moment on this end, then the twisting of this end will be more as compared to this one. We are not considering this type of a condition. We are considering that the twisting of the whole shaft will be the uniform, and we are not considering this kind of a condition. Okay, so as we are assuming that the twist along the shaft is uniform. Now we will see the third assumption, that is the normal cross section of the shaft which were plane and circular before the twist remains the plane and circular even after the twist. Now we are specifying that the cross section of the shaft is circular, and whenever you cut the shaft like this, whenever you put the cross section over here, okay, whenever you put the cross section over here, your cross section will be transverse, because it is perpendicular to the longitudinal axis. As we have explained earlier, this angle is 90 angle, and that's why this direction is known as a transverse direction, which is perpendicular to the longitudinal direction. Now if you consider this kind of a transverse plane, then the plane which were plane before the twisting remains the plane even after the twisting, and the circular cross section or the shape does not get distorted. Okay, so this is our third assumption, and for this assumption we will see another one, that is all the diameter of the normal cross section which were straight before the twist remained the straight with their magnitude unchanged. That means that the diameter is not changing with respect to the twisting. Whenever you apply the twisting, your diameter value will not be changed, or it will remain unchanged. Okay, so a little consideration will show you that the above assumptions are justified if the torque applied is small and the angle of twist is also small. Now you will have to understand that we are not talking about a shaft material which is very soft, or which is not metal, or which is less harder than the metal. We are considering the material as a metal or somewhat material which is having the strength more than the metal. So if you twist the metal and with the small amount of a torque, the twisting of the metal will be in a small amount of degrees, and that's why this type of assumptions are clearly applicable in that condition. But if you consider another material which can be distorted, which can be twisted with the minimum amount of the torque, then those assumptions are not applicable in that condition. So you will need to understand that these are not the universal assumption. It depends on the condition in which you are going to design your shaft, and it depends on the multiple parameters and variables, so that you can understand that these are not the universal assumptions. So we will see another slide, and which contains the derivation of the torque equation. Now what is the torque equation? It is the governing equation of the entire chapter. We will see examples based on this equation, we will see derivation based on this equation, we will see list of formula based on this equation, and that's why this is the base of your chapter, and you will need to understand that this can be asked in your examination into 5 to 7 marks. So this theory is also important, as well as the final conclusion of the theory will be applicable in your entire chapter. So let's first start with the derivation, and we have considered one diagram. We have shown some diagram over here in which a circular shaft is available. In this circular shaft, as you can see, this one is the fixed support, and we have fixed the one end of the shaft at the point A. At the point A, we have considered the end of the shaft fixed, but at the other end, the shaft is free. We have not any provided restriction at the other end, it is free, and now we provide the twisting moment of amount T, in this direction of the clockwise direction, at the free end, not at the fixed end. Okay, so we have considered a twisting moment at the free end, and another end is fixed. Now we have considered the length of the shaft as L. Assume that the AB line, which is straight in absence of the torque, becomes distorted. Now you need to understand that this dotted line is the condition before the application of the torque. Now we have not applied any torque. Okay, right now, currently, initially we have not applied any torque. But this is the condition of the initial condition. This is the initial condition. Now what we are going to do, we are going to apply a twisting moment of amount T. Now if you apply the twisting moment, the twisting of the shaft occurs, the torsion phenomena occurs, and due to the torsion, this straight line is going to be twisted. So this straight line will be appeared like this as a solid line. Okay, this is something like this. And the point A is fixed. And that's why the new position of the point A will be the same as the earlier position. But the point B can be twisted from the point from here to here. Its original condition was point B. Original position was at point B, and finally the point B will get twisted and it will come at the point B dash. Okay, so this is the point B dash. The B point after twisting will travel from B to B dash. Okay, so this is the final condition of the point B. Now what happens? Now we will see two different angles over here. Now this is the angle phi, which is the angle between the original line that is represented by the dotted line, and after twisting line that is represented by the AB dash line. Okay, it is the angle between the AB and AB dash. And there is another angle, that is theta, which is represented over here in the cross section view. In the cross section view you can see that there is a theta, and this theta is represented between the OB dash and OB. It is an angle between the OB dash line and OB line. As you can see, the OB line is having the radius of R, capital R, but we have considered a small radius, small r, at up to the point C. So the C point also gets distorted and twisted from C point to C dash point. Okay, so this is the basic twisting of the shaft. Now we will see the derivation steps. Two angles theta and phi, we have given the nomenclature towards them. So the first angle theta can be written as the angle of twist. It is an angle of twist. And the phi can be written as the shear strain. It is nothing but the shear strain. Okay, so whenever we want to apply the equation of the shear strain, then you can say that it is an equation of the change in length upon original length. So the change in length is nothing but the B to B dash. Change in angle is nothing but the B to B dash upon original length was capital L. So you can say that the phi, which is the shear strain, it can be written as a BB dash upon L. Now we know that instead of the L we can write R theta. Instead of the L we can write R theta, or instead of the BB dash we can write R theta. It is nothing but the relationship between the angle equals to arc length upon radius. So arc length upon radius will give you the answer of R theta like this. Okay, so this is our final answer of the BB dash, that can be written as a L phi equals to R theta. Now if you make the subject phi, then you will get the equation, that is phi equals to R theta upon L. Now we will move to another step, that is CC dash. Something like BB dash, we have taken another point, that is CC dash. And for CC dash the radius is changing, and that's why angle will be also different. And due to the different angle, we have represented it as a phi dash. And because the theta remains the unchanged, or it is a constant, and that's why we have kept it as it is, that is R theta. Now we will make phi dash here as a subject. So phi dash can be written as R theta upon L. Now shear stress upon shear stress can be written as a modulus of rigidity. Now modulus of rigidity is nothing but the tau dash upon phi dash. Tau dash is the shear stress at the fiber C, and phi dash is the shear strain at the fiber C. Now if you want to write the same equation for the BB dash, then you can directly write the in place of the tau dash, you can directly write it as a tau. Now tau dash can be written as a G into phi dash. Now instead of the phi dash we can write it as a R theta upon L. From the equation number this, we have written, instead of the phi dash we have just put the value of the R theta upon L. Now G into theta, G theta and L, all the things are constant. It is not going to change with respect to the material or any type of a condition, and that's why tau dash is directly proportional to R. Tau dash is directly proportional to R. Now if for R equals to 0, tau dash is equals to 0, and for R equals to capital R, tau dash is equals to tau, and that's why the maximum shear stress is tau at radius R, capital R. So the variation of the shear stress with the radial distance from the axis of the shaft is represented in that figure, in this figure. This figure represents the variation in the shear stress. It shows that at the radius 0, you will see the point, this point, which is the center of the circle. At this point the shear stress will be 0. But if you go at the up to maximum radius, you will find an increment in the shear stress, and your shear stress will increase like this. and you will get the maximum shear stress at the maximum radius r. With respect to r, you will get the maximum shear stress, that is tau. Okay, so this is your relationship between the shear stress and the radius. Now, what we are going to do, we are going to find this, we are going to relate those terms with respect to capital R. So, for capital R, tau can be written as a gr into theta upon L. So, this is our relationship. Now, what we are going to do, we are going to equate those terms with tau dash and tau. So, for tau dash upon small r and equals to tau upon r equals to g theta upon L. So, this is the first half of the equation. We will see another half in the next slide. Consider an elementary area dA at the section of the shaft, and let dF is the force on that area, which is represented in this diagram. As you can see in this diagram, there is a small elemental area over here, very small elemental area over here. We have kept it small so that we can easily apply the assumption on that area. The force which is acting perpendicular to that area is dF force, which is represented in this diagram over here. Now, the area of this elemental area, that is small dA. Now, the radius of this area is small r. Now, if we want to find out the torque at that area, then the equation of the torque is nothing but the force into radius, and the force which is acting on this area is dF into radius will give you the answer of the dt. That is the torque generated on this elemental area. But this is the torque on this elemental area only. We need to find out the torque for the entire area of cross section. So, we need to calculate the capital T, and for capital T we need to integrate the equation by 0 from 0 to r, from radius 0 to r, dF into r. Okay, so if you remember the value of the dF is nothing but the tau dash into dA. We have the simple equation of the shear stress, and shear stress tau dash is nothing but dF, force upon area, Okay, so dF upon dA. If you make the subject dF, you will get this equation like this. Okay, dF is equals to g theta into r upon L. We have already seen the value of a tau dash, and if you put it into this equation, you will get it like this. Now, if you just put this into the upper equation, into this equation for integration, then the constant terms g theta upon L gets out of the integration, and the remaining terms are r square into dA. Now, r square into dA represents the polar moment of inertia, and the polar moment of inertia can be represented by the j. If you put the value of j over here, then your equation will look like this. Your equation can be compared with the previous equation, and the previous equation was tau by r equals to T by j equals to g theta upon L, and this equation is known as a torsion equation. So, this is the torsion equation which we were talking about, and which will help you to solve the examples of this chapter, as well as it will help you to derive the another equations regarding this chapter. So, this is the most important derivation which can be asked in your examination, and into 5 to 7 marks, and that is why we will see one example regarding this equation. So, here is an example where you can find the data, given data. First of all, we will see that your given data indicates that a solid steel shaft has to transmit the 100 kilowatt at 160 RPM. So, this 100 kilowatt is nothing but the power, and RPM is nothing but N. N and P are both given. Now, taking the allowable shear stress. Allowable shear stress means the shear stress that can be allowed in your material without failure. So, this is the maximum shear stress. The allowable shear stress is nothing but the maximum shear stress, and maximum shear stress is given as a tau 70 megapascal. Megapascal is nothing but the Newton per mm square. Find the suitable diameter of the shaft. We need to calculate the diameter of the shaft. The maximum torque transmitted in each revolution exceeds the mean by 20%. Now, what do you mean by that? Mean torque is the average torque. So, whenever we apply the equation 2 pi nt by 60, whenever we apply this equation, P equals to 2 pi nt by 60. In this equation, we are considering the mean value, and that's why the torque which you are getting from this equation T is the mean value. So we are not finding the mean value because it is not possible that your shaft is going to rotate with the mean torque only. There may be the variation into the torque, and your torque can get increased and decreased both. But we are focused on finding the maximum torque. Why? Because whenever the loading of the torque increases, the chances of failing of your shaft will also increase, and that's why we need to find that how much maximum amount, how much torque the shaft can carry. And if your shaft can carry this much amount of maximum torque, then your shaft is safe for any working conditions. Okay, so what we are going to do, we are going to use this equation to find out the mean torque, and from this mean torque we are going to calculate the maximum torque, and based on that maximum torque we will calculate the diameter of the shaft. Okay, so first of all we will put the given values into this equation. As you can see, the only unknown which is remaining in this equation is T, and if you make the T as a subject, then you will get the answer as a 5.95 into 10 raised to 6 Newton into mm. So this is our final answer of the torque. Now we need to find out the maximum torque. So according to the given data, the maximum torque is 20% more than the mean torque. So if we want to find out the maximum torque, then your answer would be 1.2 times the mean torque. How does this come? Because we are calculating your mean torque is 100%. Okay, let's say your mean torque is 100%. But your maximum torque is 20% more than the mean torque. So what is your maximum torque? Your maximum torque is 120%. In order to remove the percentage, you will have to divide this with the 100, and this will give you the answer of the 1.2, and which we have written over here. Okay, we have written 1.2 over here. So this is the 1.2 which comes from this calculation. Now if you multiply your mean torque with the 1.2, you will get the maximum torque like this. Okay, we will keep each and every unit into the meter and mm, because our intention is to find out the diameter into mm. Now we are going to use this maximum torque to calculate the diameter of the shaft. So this is our basic equation, that is 7.14 into 10 raised to 6, that is the torque, maximum torque. Maximum torque is equals to pi by 16 tau d cube. Tau is also provided, and d cube is only unknown which is remaining into this equation. So if you make the d cube as a subject and simplify this equation by taking the cube root, then you will get the final answer of the shaft diameter as 80 mm. So this is the final answer of this example, and we conclude our lecture with this example where we have learned the concepts regarding the torsion and example based on that concepts. Okay, so in the next lecture we will see few more topics regarding our syllabus. Till then, thank you.